7s. Okay. Work energy power. Did I give you the notes already? Have I printed the work notes for work energy power? Not yet, right? I think not yet. Jaden, you have the notes?
No.
It's in the soft copy. You should be able to find it. Work energy power. It's also in part of the topic 2 notes, so you look for it. Darlene, do you find it? Something like that, yeah. And the rest of it I'll print it out for you. Okay, work energy power, which is this one here. Okay, 34 to 30, 38, 34 to 38. Oh, print. Wow, lucky you all tell me work energy power, man. I forget. 34 to 38. Maybe later today. 1, 2, 3, 4. Because work energy power, I should be able to finish the basics in half a lesson, but then I think I'll leave it to you to do practice for the rest of the lesson or for the rest of the understanding. Okay. Because here's the thing, next week, right? Next week, who is involved in the open house? You, who else? In the morning, so you won't be affected. So the two of you lah, basically, right? So I have to figure something out for the two of you in the following week. You're not involved, right? Jaden also got nothing on, right? Jaden, you're coming back for lesson next week, right? Okay. Sorry, what?
Yeah, I'm coming back for lesson next week.
Okay. Wait, 1, 2, 3, 4 first. So I think I'd rather start on circular motion today if I can, right? So I teach you this one, I teach you next one. Then maybe next week, right, for the lesson, I do a bit more practice. Right? I do a bit more practice for the circular motion questions. I do a bit more practice for dynamics questions, right? So it's not like pure content that you're missing out on. You understand this? Right? I can do circular motion next week, but if I do that, then you're missing on the pure content. So I'd rather teach the content for work energy power and I teach the content for the first part of circular motion. Okay. Sorry, I asked you which part of circular motion are they at? Do you answer me just now? Oh, so you're going on to gravitation next time. Oh, can catch anything? Can Okay. Maybe if I were to ask you some questions in circular motion, maybe you might not know how to answer. Because the way I teach is a bit different. What are you looking at? What are you looking at? Looks like a love letter, dude. Oh, handwritten some more, bro.
Old man handwriting.
Yeah. Oh man. Oh, ew, gross. Okay, I'm gonna start on work energy power. I think the first thing I want to do first is to foolscap paper and then draw this thing out, right? So I'm gonna ask you a couple of questions, guys. This is a box on a smooth table, right? Smooth table, right? Because I'm gonna ask you the obvious things. You all should know some of these already, right? The force is 50 newtons, and the distance pulled is 8 meters. Right, distance pulled is 8 meters. What's the work done by the force? What's the work done by the force? I also don't know how to do this in my head. I don't know how you all do it. 120, yes. 120. What's the units of work done? Joules. Remember this, our work done is energy, energy is work done. Okay? Alright? Work done is energy, energy is work done. And I'm with the force is with me. Okay. Different scenario now. 50 Newton force. This time around there's a friction of 4 newtons. Right? Then hopefully you remember how to do this. Okay? Question, what's the work done by the force? Alright, work done by the force. Come. Wait, let me give other people a chance. Right, what's the work done by the force? Still 120 joules. Oh, did we do this last week? We did this last week lah. Then there's not me. Hey, then you say lah. Then I just repeated myself like an old man, right? Okay, where did I stop at? How you staple your notes that you staple at the bottom one?
Accident.
Okay, come tell me where did I stop at last week? I stopped at somewhere. I stopped somewhere. What? Did I do the half mv square minus half mu square?
Yeah.
Did I do the half fs? Sorry, did I do the fs equals to cosine theta? This one, the work done equals to fs cosine theta.
Oh.
No, I haven't gone through this one yet. I haven't gone through, but I've gone through the work done equals to half mv squared minus half mu squared. Did I do this? I did this, right? I asked you to memorize this, right? Did I give you the then you sure you don't have the notes? Oh, I'm gonna kill you all, no, seriously. I'm gonna kill all of you. Wow, I'm gonna kill all of you. I see two set of notes of the same kind now. I'm gonna murder you. I'm gonna kick you, no, seriously. Ah. Okay, fine. So which part of so what's the last thing you copied down for work energy power? What's the last thing?
Half M.
No. What's the last thing? I don't wanna listen to you. You're not even looking at your old notes. Come, Darlene. What's the problem that they sent? Oh, the thing that dropped into the snow one. Okay, the guy that fell in the snow. Did I do this? Did I give you a diagram for this one? Did I do a diagram for this one?
Yeah.
Did I? Can you just flip around and let me see the diagram? Just want to make sure. Okay, can. Okay. Oh, and then I did the angle also, fx cosine theta, right? Component of the force, right? Fs cosine theta, yeah, component of the force. Okay, I've done all that already lah. So what am I doing now? What am I doing now? Hang on, so I've done that all already. So I've done a bit of work energy power already. Did I do the work done in springs? Not yet, not yet. Okay, hang on, but before I go into this one, okay, come. Listen up, guys. I got a car, right? The driving force is okay. I'm a bit scattered brain today because I think I didn't sleep well. The car thing later. Let's finish our work done in springs first. Okay. Sorry, did we do this the last time round? F equals to kx for the spring. We didn't do this. Yeah, the spring constant, right? You recognize this, right? What's x? X stands for what? Extension. Good. So you know what this is. So when you have a spring, right? If you have a unstretched spring, then you hang a mass on it and it stretches, right? Then it stretches by x extension, then the force equals to kx, right? The weight here is equals to the force in the spring, F equals to kx. Agree? Do you understand this? We did this, right? The question is, what's the energy stored in the spring? To find the energy stored in the spring, you can look at the graph, right? F and x, right? This is the graph, F and x, right? When you hang a certain amount of mass, it will have a certain amount of extension. Agree? Right? If you hang a certain amount of mass, right, of a certain weight, okay, then it will have a certain amount of extension. Right? Draw this graph. Yes, draw this graph, guys. Right. So there'll be this amount of extension. Then you draw one line across, like this. Okay. And the amount of energy stored in the spring is the area under the graph here. The amount of energy stored in the spring. What's the name of the energy? Elastic potential energy. The EPE will be the area under this graph here. Right? This will be the EPE. Okay, this will be the EPE. Good. All right. Okay lah. Easy stuff lah. You all know this. So the EPE is equals to half F times X, right? Half of the force times the extension. Again, X stands for extension, not the length. If they give you the length, you must minus away the original length. If they give you the total length, you must minus away the original length to get the extension. Right? Keyword is extension. Always remember it's about the extension, half fx. Now I want you to sub out this f for the kx, and therefore what's the equation? Sub f inside. Half kx squared. Good, right? So half kx squared. So instead of f, if you have the spring constant, you have the extension, you square the extension, you will get the area under the graph also, which is the EPE. Okay so far? Good. But here's the annoying thing. They don't like to ask this question. They like to ask something else. They like to ask this. Right? Let's say this is x1 and this is f1. Okay? Let's say you add on another mass and the extension increase. Right? Let's say the new extension is here, x2. Okay? So in order to increase it to x2, you need f2, right? Then they want to ask you, what's the additional energy or what's the additional work done to extend from x1 to x2? Additional work done to extend from x1 to x2. Right? What's the additional work done? Right? And the additional work done is half kx2 squared minus half kx1 squared. Right? Does this look familiar? Does this format of equation look familiar? Yeah, it looks familiar, right? It's like the half mv squared minus half mu squared, right? Again, a reminder is this. Do not go and find x2 minus x1, then you go and square that, right? Don't go and find half k x2 minus x1 squared. It's supposed to be half k x2 squared minus half k x1 squared, right? It's just like the difference in ke. Okay? Good. You know, okay now? Awesome. Okay, okay, so I'm done with spring. I mean, this is like the most common annoying question they like to ask, right? Just a recap. What's the name? What's the law for this equation? There's some law for this guy. All right, I help you remember. You have a spring, you have a hook. Hook's law. All right. When you have a spring, you have a hook, right? Hook's law. Okay. All right. So in case you cannot remember the name, it's Hook's law. Now Hook's law tells you that f is proportional to x within the limit of proportionality. I don't know whether you've seen that in your notes, right? Within the limit of proportionality. Okay, what does that mean? It means this, for spring, right? Okay, the extension is proportional to the force that you apply on it. Okay, within the limit of proportionality, that means within the line being still straight. At a certain point, right, this graph will not be straight anymore. This graph will start to deviate. The graph will start to deform like that. Okay, so in a sense, the limit of proportionality is somewhere here where the straight line ends and it starts to curve away. Right? Why is that? Because springs, right? Springs tend to deform after a certain amount. Like if you stretch it too hard, right, it will be bent out of shape. Okay, so Hooke's law only applies to this straight section here. As long as it's proportional, then it's valid. Right? In case you're trying to understand the definition. What? Hooke's law? Definition of Hooke's law? Okay, thanks. Hooke's law states that force is proportional to extension within the limits of proportionality. Within the limits of proportionality. Okay, that's it for springs. So if you need to calculate anything about like, okay, I'll give you an example. I have, let's say for example, a steel ball rolling down the hill and going to hit a spring like this, right? Going to compress a spring, something like that. Then they ask you calculate the amount of compression on the spring, right? It's just basically, right, the GPE being converted into the EPE, right? Assuming no frictional losses, whatever GP you have here will be converted to KE here. Then the KE here will go over and compress the spring, right? Then you can just use MGH to half KX squared. Okay, then you can calculate the compression. Don't forget X also stands for compression. Okay, good. And that's straightforward lah. Draw the ball, draw the equation, draw the energies. Right? GPE, EPE, right? MGH, half KX squared. Okay, let's do the car thing now. Oh, but before I do the car thing, let's understand what's power. Okay, so I close this now. Right, power. What's power? Definition of power. Okay, rate of work done, or energy consumed per unit time, or energy produced per unit time. Power is just energy per unit time. Right, that's what power is. Right, power is rate of work done. Rate of work done. Okay, which is equal to energy over time. What's the units of power? Yeah, exactly. And I was telling you what's the units of power. Okay. Let's say you see 1,000 watts. Right? Let's say you see 1,000 watts. What are you supposed to think of? 1,000 joules per second, right? So the way I train the sec force, right, is like that. They see 1,000 watts, immediately think of 1,000 joules per second, right? It means every time you see 1,000 watts, every time you think about it, 1 second will get 1,000 joules, or you will use 1,000 joules. Okay? No issues? This one should be quite straightforward. But you must also remember a couple of things. Let's say for example, right, I give you a completely non-work done kind of question. Let's say I have a mass of 50 kg, right? And I raise it up by 8 meters, okay, in like 10 seconds. What's the power of the motor? What's the lifting power? What's the lifting power? 50 kg, 8 meters in 10 seconds. What's the lifting power? Right? So power is energy over time. So when you lift this object up, right? Okay, you have to consider mgh over t, right? The key thing that you must take note of is that it is constant speed, right? It must be constant speed. Why must it be constant speed? Correct. So constant speed means no gain in KE. Is there KE? Is there KE? There is KE. But if it's constant speed, is there a gain in KE? No gain in KE. So the work done to lift this object doesn't include the KE portion. It's only just mgh over t. If you tell me that the object gains KE, right, as it's being lifted, then you have to add in the lifting power plus the amount of KE that it gains. Right? I mean, I can add that in a while, but let's just do the simple one first. What's this? What's the lifting power then? You just got mgh. Now you have to use 9.1 already, right? mgh, right, over 10 seconds. Right, so 50 times 9.1 times 8h, and then times divide by 10 seconds. Right, 390 watts, right? 2SF, right? 2SF, 390 watts. Okay, that's the lifting power, right, at a constant speed. At a constant speed. Right, like I say again, if it gains speed, you have to add in the KE, the gain in KE for the lifting power. Right, but it didn't gain speed, so we say constant speed. Do we understand this? Okay, now, so the next thing is, what kind of things can lift this object? A, a crane, right? A crane, right? A crane, yes. Okay. So when we deal with work energy power, right, we usually try not to use force. Okay, so there's a crane that lifts it up like that. Right, the crane is a motor, right? The crane is a motor. So let's say I tell you that this motor is a lousy motor, it's a 40% efficient motor. Right? It's a 40% efficient motor, right? Then the next question is this: how much electrical power is required to run this motor? So we're dealing with efficiency now. So the motor can run at 390 watts to lift this mass up, but it's only 40% efficient. So how much electrical power does it need in order to work this 390 watts power? Okay, so electrical power required, right? Electrical power is equals to, right? Electrical power required is 390 divided by 0.4. Right, 975 watts. 975 watts, everyone? Okay, I'm going to stop you here. Okay, so what I'm going to do is I'm going to show you how some students make careless mistakes in a sense, right? They may tend to do this. Some students may tend to take, okay, if you tell me that it's 40% efficient, right? Some students do this, they take 390 times 1.4. 390 times 1.4, right? Because they think it's like, they need to add on the 40%, right? So 390 times 1.4. This is wrong, You must understand why this is wrong, okay? I mean, this is literally primary school math, right? Percentages, right? So 390 is represented by the 40%. 40% of the motor is 390. So the question is, what's the input? The input will be 975. Right? What happens to the difference? 975 minus 390, what happens to the difference? Heat and sound in the motor lah. Motor. Alright, so we call it the motor. Right? So you just say in the motor, in the moving parts of the motor, right? 975 minus 390. Are we okay on this? Quite clear, huh? Good. But I didn't really tell you what's the definition of efficiency, so can you tell me what's the definition of efficiency then? Useful, either energy or power, it's fine also. Useful E or P over total, right? Energy slash power. Okay, so it can be either energy or in power, right? So you can also see that if you want total, you take the useful, you divide it by the efficiency. Right? You take the useful, divide by efficiency, you can find total that way. Useful, useful over total. I want you to memorize it. Useful over total. What's the most common mistakes? Students will say efficiency is total output over total input. Wrong. What's total output over total input? 100%. Right? 100%, because total output includes both the useful and the useless. For the motor, what's the useless energy? Heat and sound. Right? The useful was the MGH. Right? That was a useful energy for the motor. So efficiency is based on useful energy only. Useful over total. Right? Lock it in your head. Useful over total. Don't go and say total input and output. Right? That's completely wrong. We good? Moving on. Move on. That's okay. Okay. Right. So that will be for efficiency. Right. Let me manipulate power now. Power is equal to work done over time. Work done is force times distance over time. Split the equation, force times distance over time. power equals to force times velocity. Right, write this down. So for a moving car, power is equals to the driving force times the velocity of the car. Right, I'll give you a couple of scenarios on how to use this equation. Then you understand how to use this lah. Okay, can I show you? Right, I'm gonna close this now. Right, I want to draw something. Hey, you write down already? Power equals to force times velocity, yeah? Okay. Let's say I have a car, right? Let's say the car went from like 8 meters per second, right? And then it accelerates all the way to, let's say, 10 meters per second, right? As an example. So as an example, let's say I wanted you to find out 9 meters per second, right? Let's say the driving force was like 5,000 newtons, right? Can I get you to understand that if you want to find the power of the car, right? If you want to find the power of the car, it was basically force times velocity, right? It's force times speed. So it does not have to be a constant speed, you know. This speed doesn't have to be a constant speed. It just can be the speed at this instant in time. Let's say you want it at 8 meters per second, you just sub in the 8, then it will be 5,000 times 8. If you want it at 9, then it's 5,000 times 9. If you want it at 10, then it's 5,000 times 10. The power is increasing, right? Which makes sense because, you know, in order to get faster and faster, the power of the car must increase, right? So car engine, right? Maybe you write down on one side, car engine, right, can be constant force or constant power. Okay, so when you're solving any questions, some questions when they tell you, hey, the force is constant, right? They tell you constant force, the driving force is 5,000. Okay, it is possible that the force is constant, but the power of the car is increasing. You hear what I just said? Because this is the part that confuses a lot of students. Like, how come the force can increase but then the power is constant? Oh, sorry, the force is constant but then the power can increase. Can, because the speed is increasing, right? So I want you to remember this, right? So if it's constant force, the power can increase. If it's constant power, the force can change also. So don't go and relate force and power directly. Don't go and say that, oh, constant force means constant power. That's not true, right? So force can increase, power can increase, but maybe the velocity change. So all these three terms can change, right? So don't assume that when you have constant force, it will be constant power. It's not true at all, right? Constant force, you just take it as is. Constant force, that means it's really 5,000 newtons. Okay, on this? I'm going to give you a scenario now, right? So I'm going to close this, right? So the scenario is this, right? This is one of their most popular one. I have a car, the driving force is 8,000 newtons. This is the driving force, 8,000 newtons. Right now, the car is traveling at a max speed of 7 meters per second, right? This is a max speed of 7 meters per second. Then what's the power of the car? Straightforward, right? 56,000 watts, right? 8,000 times 7, 56,000 watts. Correct or not? No problems there. Okay. Next question though. Right. Is there a resistive force? And assuming there's just air resistance, is there a resistive force? Yes or no? Why yes? Almost there. Almost there. Good. Good. Okay. A bit more details. Why is it equal? Almost there. Anyone want to help him out? Tell me now, velocity means what? Resultant force is 0. Okay? Alright. So Vmax actually means the acceleration is 0. Right? Maximum velocity, right? So acceleration is 0. Acceleration 0, resultant force 0, then it means that the air resistance is 8,000 newtons, right? 8,000 newtons. Agree? Now, what happens if you want to drive faster? What happens if you want to drive faster? How to reduce the resistive force now? You what? Let's say you want to drive at a greater speed, a greater maximum speed of 9 meters per second. What do you think will happen, guys? You need more power. Either you need more power or you need more force, right? Okay. To do what? Okay. Okay. What I'm trying to get at is this: when you have a higher Vmax, what happens to the air resistance? Why does it become higher? Okay, yes, you're saying that the air resistance is proportional to the speed, right? You're saying that the air resistance is proportional to speed. Okay, good. So I'm gonna tell you this, okay? They can I ask you either of these three ways. Okay, so these are the possible questions they can ask for this one. This one they tell you that the air resistance is proportional to v squared, right? Or they tell you is constant power engine, or they tell you there's constant force engine, right? So right, constant power engine or constant force engine. Okay, let's go with number 2 first. Let's talk about constant power engine. That means this engine is able to provide a constant power, right? So which values doesn't change? Yeah, that means this value don't change. If let's say they tell you constant power, why not? If they tell you constant force engine, which value doesn't change? The 8,000 doesn't change, right? That means that the 8,000 car doesn't change, right? Or if they tell you that the resistive force is proportional to v squared, right? Then this resistive force will increase accordingly, right? How about this then? Okay, tell you what. I want a new Vmax of 9 meters per second squared. 9 meters per second, sorry. New Vmax of 9 meters per second. Can you tell me what's the new air resistance? Huh? No lah, what? Yeah, don't forget, air resistance is proportional to V squared. Is proportional to V squared. What's going on here? Air resistance is proportional to V squared. What's the new air resistance? Okay, if you don't know how to manage this kind of relationships, and let me teach you one quick method, okay? Okay, you see this proportional sign? Get rid of the proportional sign. How do you get rid of proportional signs? Yeah, I know you put equal. Then equal what? So equals to what? How come you all don't know how to do this? This is math, eh? Think math. If I tell you that's proportional, then what do you do to make it to an equation? Yeah, times the constant lah. Kv squared lah. Yeah. Okay. So from the first instance, this is 8,000 and this was 7, right? Can you find out what's k first? Find the k value first. Okay, so if you don't know how to do this using like those kind of ratio method, right? Proportional method, hey, write this down. Right? Find the k value. 快点. The k value would be 7 squared over 8,000. Eh? No. 8,000 over 7 squared. What's wrong with me? 8,000 over 7 squared. And then your new air resistance at 9 meters per second, you use the same k value times 9 squared. Yeah. So 8,000 over 7 squared times 9 squared, right? There you go. This is how you do the, if you don't know how to do proportional or the ratio method, then I suggest you use this method, all right? So every time they tell you it's proportional to something, right, write down this equation, right, equals to k v squared, like that. What do you get? 8,000 over 7 squared times 9 squared. 13,200, okay? 13,200 newtons. This will be the new air resistance if you want to travel at 9 meters per second, right? Much higher, right? From 8,000 jump to 13,200 newtons. Good. What will be the new power of the car? What will be the new power of the car? Because if this is the new air resistance, right, and you want it to be at the new Vmax of 9 meters per second, then your new driving force is also 13,200 newtons. Right, and therefore the new power will be 13,200 times 9. Yes. Right, 13,200 times 9. Wow, what a weird number. 1.46 times 10 to the power 6 watts. Huh? Oh, no. Sorry. I got this wrong. 13,200 times 9. Sorry, 118,800 watts. Right? 118,800 watts. Right? From 56,000 watts becomes 118,000 watts. Okay? Good. So this is one of the higher order kind of questions when it comes to power. T equals to FV, right? With maximum velocity, right? With air resistance and driving force. This is actually quite a common question, right? And if I were to set an exam, I'll definitely set this question. Yeah, always, right? Because I want students to get confused by this thing here. Okay, one more question. Can you describe the overall energy change for this car? Can you give me the overall energy change for this car? That means you have to describe in words, not calculate. What's the type of energy to what kind of energy? So the car burns what? Chemical potential energy, right? Then what does it ultimately become? Wrong. Not KE, right?
Heat and sound.
Yeah. Yes, very good. All right. So this is maximum speed, right? This is constant speed, right? Constant KE, right? That means whatever CPE that the car burns, it's merely to overcome air resistance only. So the CPE becomes heat and sound. That's it. It does not become KE. Because if you suggest that it becomes KE, then the KE should increase. But at maximum speed, the KE didn't increase. So it's CPE, right, to heat and sound, direct. Okay. So some of the homework trackers that I sent you for topic 2, right, includes work energy power questions as well, right? So get those done. Your schoolwork should have some work energy powers too, right? So try to get started on those because I think most of you already finished work energy power from in school already, right? Jaden, your school suddenly slowed down a bit. Any reason for that?
It's a holiday, right?
Oh yeah, school holiday right now. Yes, that's right. They got 2 weeks, right? Last week and this week, right? This coming week also school holiday, right? Yeah. Yeah, I know. Yeah. They follow the SGI's international follow all your syllabus, but then their holidays are different. June, how many holidays? How many weeks holiday do you have? June?
A month, I think.
Ah, June also you get 1 month, eh? Oh yeah. Summer
Yes, like
holiday should be
December
long,
is the
right?
shorter one.
Oh yeah.
December is shorter one.
Okay, what? Who you calling down? Okay, all right. Anything else I want to do here? Hang on, let me think about what are the questions I want to go through here. These are, I think usually these are okay lah. You just need to try. I just try the questions, right? So I don't want to go through any more questions here already. Like I said, I really want to go through the content. So let me go through the content for topic 6. Right, I'm really done with topic 7. Topic 12, sorry. What am I doing? Topic 2. I'm done with topic 2. I'm done with the whole thing already. Anyone has any more energy questions?